Hi, and welcome back to Applied Machine Learning from Analytics Vidya. So far, we have covered the linear models and the generalized linear models, and how gradient descent can help us in order to find the right optimal line in each of these algorithms. Now, in this video, we'll be looking at another algorithm called logistic regression, which is actually a classification algorithm. Now, you might be thinking that given that this is a classification algorithm, why is it called a regression? And I would just want you to stay with me for some time, and I'll bring that out in a short while. So let's start understanding logistic regression by taking a very simple example. So let us consider this plot, which depicts a small population of children with their ages on the x-axis and whether they have a smartphone or not on the y-axis. So it is a classification problem, and we want to predict whether a person would have a smartphone or not based on their age. So let us try and use the same method which we used in case of a linear regression. So we basically fit a line and then see if we can classify using this line. When we draw this line, ideally the values should only be 0 and 1. But when we draw this line, what we see is that while there are some values between 0 and 1, and we can put a threshold like if the value of age is below this particular point, the person does not have a smartphone. And for a particular value above age, it will have a smartphone. So we can do something like this, but the minute you add more data points, you'll see that the slope of line changes, and we'll need to inadvertently move the threshold. So it doesn't give us the right way to classify a particular problem. So my threshold of age cannot move in a predicting algorithm. So that's a problem. The other problem is that when you extend this line, it will inadvertently have values above 1 or below 0, which do not mean a lot in case of our classification problem. I don't know what values above 1 would mean or values below 0 would mean. So it's not a natural extension of the linear regression, and there are challenges with interpreting this model at the extremes. So that is where logistic regression comes in. So let's try and build logistic regression. So let's say that we have the equation of this line, which is z is equal to beta x plus b. So the properties, we are already aware of the properties of this line. Now what I actually need is a function of z which transforms this line into something like this, where the values are between 0 and 1. And this is where a sigmoid function, which is also known as a logit function, comes in handy. So what this function does is it transforms this linear line into a curve which looks something like this. So it is constrained between 0 and 1. So there are a lot of interesting properties of sigmoid function, which we'll cover in a later video. But what it basically does is it transforms this linear line, which is the blue line, into a line which has values between 0 and 1. And it is asymptotic. So irrespective of how many values I add towards the end, the value would remain constrained between 0 and 1. Now we can apply this sigmoid transformation to our linear line z and actually run a classification problem. The other advantage of this is that the predictions which we'll get from this are all continuous in nature. So we can use them as probability for making the prediction. So for example, if a person is on the extreme right, the probability is very close to 1. If the person is on extreme left, the probability is actually very close to 0. And in between, you can get probabilities which tell what is the probability of a person having a smartphone. In addition to this, everything else remains the same. So as long as I can find values of beta and b, and that is where we use gradient descent, I can use this algorithm to do classifications, and everything which we have discussed till now in linear regression basically stays the same, except for one thing, which is the cost function. Now, the cost function which we had used in case of linear regression was something like this, which is y hat minus yi iterated over all the data points, and then you do a square. So this was the cost function which we used, and it was a convex function. The y hat that we have covered is a non-linear function, and when we use this y hat in the above equation, it will be a non-convex function. It would unnecessarily create complications if we use gradient descent in this particular scenario. So what we do is we change the cost function, and the cost function which we can use is the log loss formula. So you would have seen log loss as an evaluation metric. So we can use the same log loss function as a cost function, and that gives me the continuous function which I am looking at. So this is the log loss formula, and I have replaced the PIs with the yi hats. So when the actual class is 1 and I am looking at the probability of class 1, then the left part of the equation is active and the right part becomes 0. The curve in this case would be like the one shown on the screen. So when the actual class is 1 and the probability of class 1 is very close to 1. So when you go towards the side of the curve, my cost almost reaches 0. And when I move away, my cost keeps increasing. Similarly, when my actual class is 0, the right part of the equation becomes active, while the left part vanishes. When we plot this, you'll get a graph like the one shown on the screen. So when the actual class is 0 and I'm predicting 0, the cost is 0. And as we move away, the cost keeps increasing. And we add both the parts, which gives us the right cost function. And y hat predictions can be obtained by using this equation. So we use the cost function to get values of beta and b, which can then be plugged in into this formula, and we can get our predictions. So that's how we'll use the gradient descent. So the cost function is outlined over here, which is represented by j. Once done, we can differentiate it with both the parameters beta and b. So this we have already seen in linear regression. I'm just repeating so that everything is clear. And we can use these to update our parameters. So once differentiated, this is the formula which they come to. And we can use this to update beta and b to get the final convergence. So that is how we'll run logistic regression. In the next video, we'll look at the implementation of logistic regression. Thank you.